Good afternoon. Here we are talking about chapter 3 in the textbook. And chapter 3 is on hydrocarbons. And hydrocarbons, we have a couple examples up here showing the functional groups. We have the alkane, ethane, so it has the ane ending because it's all sp3 hybridized carbons. We have the ethene, or ethylene, where we have an sp2 hybridized carbon connected together with a double bond. So the ene, ethyne or acetylene, has the triple bond in between the two carbons, so sp hybridized. And then we have benzene, the aromatic ring with the three alternating double bonds in it. And be careful that for it to be aromatic, it has to have the three double bonds in it. It can't just be a cyclohexane. So careful about that as you're looking at things. Now, here on the structure shown below in the bond line drawing, we have one, it's an alkane, and in ethane or in any alkane, it only has sigma bonds. There are no pi bonds. So in this, we have we'll draw the methyls with red hydrogens. So we have three primary carbons. They are carbons with only one bond on them. And then in blue, we'll show the secondary carbon with its hydrogens. A secondary carbon has two bonds off of it. And then in green, we'll show the last hydrogens. And there's one tertiary carbon with the one green hydrogen on it. So a tertiary carbon has three carbons off of it, a secondary carbon has two, and a primary has one carbon off of it. So we need to know our alkanes. So methane, ethane, CH3, two carbons, so it's just a line. Propane, CH3, CH2, CH3, it has 1 point. Butane, CH3, CH2, CH2, CH3 with 2 points. Pentane, is 5 carbons. Hexane has 6 carbons. 4, 5, 6. 2 methyls on the end. And then heptane has 7. 3, 4. Octane has 8. We'll just draw the molecule. 1, 2, 3, 4, 5, 6, 7, 8. Nonane has 9. And decane has 10. In it. So those are the different hydrocarbons. You need to know what each of these are for 1 to 10 carbons so that you can name things as we're going along. So for nomenclature of alkanes, we need to follow the rules of how many carbons, 1 through 10. Then the parent ends up with the name ending in ane because it's the parent name. And then if it's a substituent off of something, we drop the ane and add yl. So a methyl is a CH3 as a substituent off of something. So we have to, 1, number the longest chain, then use the numbers from B to designate the locations of the substituent groups. When 2 or more substituents are present, each gets a number, every one of them, even if they're on the same carbon. So we'd have a 2,2 dimethyl or something like that. It's not just one number for everyone. We have to give that number twice. If we have multiple ones, we have to give a prefix of di, tri, tetra. When two or more chains of equal length compete for selection as the parent chain, choose the one with the greater number of substituents. When branching first occurs, equal distant from each end of the longest chain, choose the name that gives the lower number to the first point of difference. Okay, so we'll try this on some of the compounds on the next page. So we number these 1, 2, 3, 4, 5, 6. If we go left to right, if we go the other way, we'll label it in blue. 1, 2, 3, 4, 5, 6. Okay, so if we count the red way, we have, whoops, let's make it red, sorry. We have these 3 methyls. They would be on a 2, a 3, and a 5 trimethyl. If we count the blue way, it would be a 2, 4, 5 trimethyl. We want the substituents to have the lowest number possible, so the correct way to name this would be go in the red direction, so a 2, 3, 5 trimethyl, and then it is a 6 carbon chain, so it would be a 2, 3, 5 trimethyl hexane. Okay, and that part wouldn't change either way. When we go to the next one, we have a substituted butane, and this butane has 4 carbons off of it, so it's going to be a 2, 2, 3, 3 tetramethyl butane. Then the last one here, we could number it 1, 2, 3, 4, 5, 6, 7, 8, or 7, 8 this way. Okay, when we number things, we want to have the substituents with its smallest amount of branching and all as possible. So the best way to number this one is this way, where we have a methyl and an ethyl off of it, instead of if we numbered it the other way, where we'd have the isopropyl off of it. So keep the groups as small as possible if the chain is the same distance. Now if we number it that way, we'd have a 4, 7 dimethyl and a 6 ethyl. Whereas if we numbered this blue way, starting the other direction, we'd have a 2, 5 dimethyl and a 1, 2, 3 ethyl. So we can see from the numbers that the correct way for this one would be the blue way. So 3 ethyl, 2, 5 dimethyl, and then it's 8 carbons, so it is an octane. Now with nomenclature, the spelling is important, so if you spell it wrong, it is wrong, because it's hard to do partial credit on that part. Okay, so make sure you're careful about your spelling. For a cycloalkane, the only change we have to do is number the substituents off the ring in alphabetical order, and we call it a cyclo in front of the alkane. So this would be a cyclohexane, because it's a 6 carbon chain, and it has a methyl and an ethyl, so we need to number the ethyl first because it goes alphabetically. So this would be a 1 ethyl, and then we'd need to go 1, 2, 3 methyl cyclohexane. Okay, and we want to have the substituents as small a number as possible. That's why we need to go 1, 3. Instead, if we went this way, it would be a 1, 2, 3, 4, 5. So it would be a 1 ethyl, 5 methyl. So the substituent is much larger if we go that way. So we wouldn't want to do that. and that one. So here we have a methyl and a isopropyl, or a methyl ethyl. So 1 isopropyl, 3 methyl cyclohexane. The next one would be a 1 ethyl, 3 methyl cyclopentane, because it's a 5-membered ring. The next one, 1, 2, 3, 4, 5, 6, 7, would be a 1 butyl cycloheptane. And the last one, 2, 3, 4, 5, 6, 7, 8. Doesn't matter which way we number, we're going to get a 1 and a 5, no matter how we number it, which way we number it. So this is a 1,5 dimethyl cyclooctane. So there are two O's there because you have the cyclo O and the octane O. So make sure you get both of those in there as you're going along. The bicycloalkanes, we need to count the number of carbons in the bicyclic system, starting from a bridgehead, number around from one bridgehead the longest way, then the next longest way, then the shortest way. So this is a heptane because there are 7 carbons in it, so it's a bicycloheptane. And then in the brackets we have to say 3 because there are 3 carbons this way, 2 because there's 2 carbons this way, 0 because there's no carbons between the bridgehead this way. So this would be a bicyclo 3,2,0 heptane. Now, when we look at this, remember what I said, we have to start with a bridgehead, and that's a carbon that just has all the 3 rings attached to it. 1, 2, 3, 4, 5, 6, 7, and count around, and you have to keep going. You can't jump around. So this would be a 2,7 dimethyl, 3 ethyl, 2,7 dimethyl, bicyclo, 3,2,0 heptane. Now this one, this is our first substituent.
Could you try again?
It needs to be the lowest it can be number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a 10 ethyl, 2 methyl, bicyclo. Then there are 10, so there are 3 carbons in the one with the methyl bridgehead between. There's 3 that way, so this is a bicyclo 3, 3, and then there are 2 that way, 2 decane. Okay, and then the last one, start at a bridgehead, we have to go the long way, so that's 1, 2, 3, 4. Then we get to go to the methyl and then the final one. So this is a 5 dimethyl bicyclo 2,1,1 hexane, because we have 6 carbons. Okay, so and the bicyclic ones, there will only be maybe 1 question of those on a test. There won't be very many of those. primarily it'll be the straight chain ones, maybe a couple of the cyclic ones, and maybe on an off chance one bicyclic compound in there to name. But there won't be a lot of bicyclic ones. So structure and conformations of alkanes. Now at this point, if you have a model kit, get your model kit, bring it to class. We'll talk about it. It'll make it a lot easier to see the things going on if you have your model kit. So we know ethane, 2 carbons, 6 hydrogens, a carbon-carbon single bond. If we draw ethane with the wedges and dashed bonds showing what that is, the carbons and the 2 hydrogens, those are in the plane of the iPad or of the board or of whatever you're looking at, the screen. Okay, so those 4 atoms are in the plane of the board. Then this hydrogen and this hydrogen, the blue, are behind the plane. And then the green hydrogens are in front of the plane. So they're coming out towards us from the plane of the screen. Okay, so we have to be careful that we show all of that as we're going along. Now, if we were to pick this molecule up, ethane, from the way it is drawn right there, and I'm going to erase the marks I made on it so we can talk about it as we're going along. Okay, but if we were to grab it by this bond and put our hand around that bond and then rotate our hand 90 degrees, what we're going to do is we're going to think about looking at it from right here, this end. Okay, so if we think about grabbing that with our hand around that green bond and rotating it 90 degrees so we can look down the bond, we would see the molecule as it is drawn there on the next part. Okay, and what this is showing is this carbon is this carbon in the front, so it's in the front with the 3 hydrogens. 1 hydrogen is going up, 1 hydrogen is going up, then a hydrogen is going back, that's blue, that's this one, and then a hydrogen is coming towards us, that's that one. Okay, so as we look at this, we have to think about what do we have and where is it in space. And this is why it can be hard to see what you have two-dimensionally until you get the models and play with it a little bit and get it to be able to rotate it around in your head of what we're showing. Okay, now I will always write all of this stuff out so that it's easier to see what's going on. Now, this carbon back here, the green one, is the circle. It's the carbon in back. So the carbon in front is the dot in the middle of the circle, and the carbon in back is the circle when we draw things like this. Okay. Now, if we were to think about this molecule, we could put our little eyeball right here and draw the Newman projection for what we see. So we start with a circle with the dot in it. The bromine on the carbon in front is going straight down. Then we have the hydrogen coming towards us and the hydrogen going back. As we look at it from where our little eyeball is right here, looking towards that. So then on the carbon in back, the red circle, we have the methyl going straight up and 1 hydrogen down to the back and 1 hydrogen down to the front. Okay, so that is showing the Newman projection for what we have there. And sometimes the the Newman projection makes it a lot easier to tell what's going on and what do you really have in the solution. So if we look at the next one and also put our little eyeball here and look down that bond, looking at what we have on the carbon in front, the hydrogen going straight down, the carbon in back, the methyl going straight up. On the carbon in back, we have a hydrogen, this hydrogen, to the right, and the other hydrogen to the left. And then on the carbon in front, we have a hydrogen to the left and a bromine to the right. Okay, so as you're looking at these, think about where you would position your eye to view down the bond and figure out which bond you need to look down as you're going along. Okay, and we will practice a few of these as we're going along. So which of the following conformations of ethane has the lower energy? And in ethane, remember, we have 3 hydrogens on each carbon, so all of these little sticks out here is a hydrogen. It's not just a little stick, it takes space. So if we draw them all in and think about it, the one on the left has the hydrogens more spread out, so it's going to be a lower energy than the one on the right. Okay. Then the next thing, we have the conformations of butane, and we want to label them from lowest to highest energy. So this one, is the lowest energy because the methyls are as far apart as they can get. This one is going to be the highest energy because the methyls are as close together as they can get. Then we have a methyl to hydrogen in this and a methyl to hydrogen in this one. So those are going to be close together, so those are going to be tied. And then we have these where the groups are farther apart. So this one is total eclipsed. These are eclipsed. And then 2 is gauge. Okay, so there's the order of energy wise. So if we look at this bond rotation, the first one, anti, is here. Then the fourth one is the highest. Then the third one over is lower, and the second one is higher. And so the third and fifth are the same height, and the second and sixth are the same height. And then you just think about the mountain range that goes in between those, and that's the bond energy, potential energy diagram for the bond rotation around that. And it doesn't matter what these two groups are, the two big groups, we're not looking at the exact energy level, we're looking at the change in it as we rotate it around, which one's higher, which one's lower. So it doesn't have to be perfectly to the exact energy change. We just want to see the overall scheme of it. So can you make a model of the chair form of cyclohexane? Can you draw the chair form of cyclohexane? The easiest way to do it is to draw the armrests, and then from the armrests, if you make them at a slight angle, go up from the ones down and down from the ones that are up, and there you have the chair form of the cyclohexane. From the carbons that are going down, we draw a group going straight down. From the carbons that are up, we draw a group going straight up. Okay, so those are the axial groups. They're either going straight up or straight down off of the carbon. So the little red dots are the hydrogens that are going straight up or straight down. Then if we change to a different color, the blue is parallel with the angle 1 removed from it. So those two hydrogens, this one's parallel to the armrest, this one's parallel to the armrest, and then these are parallel with the one across from it. Okay, so the blue groups are all the equatorial groups. Okay, and it just takes practice in trying to draw it and getting good at it. It's not something that comes easy. Okay, and the chair form of the cyclohexane is the lowest energy form of cyclohexane because the bond angles are as close to the 109.5 as you can get, and the groups are as far apart as you can get. So of these two monosubstituted cyclohexanes, with the methyl equatorial, it's more out from the edge of the molecule, further away from everything. So this one is going to be much lower energy than this one, where the methyl is very close to the hydrogens 1 and 3 from it. Okay, so now on the last one here, cis or trans disubstituted, we have a methyl up and a methyl down, so they are trans to one another. We have this methyl down. This methyl is down because this hydrogen is up on that carbon, so they are both down, so they are cis to one another. This methyl is up, this methyl is down, so they are trans, and these two methyls are both up, so they are cis. So you just have to look at it, draw it out, and make models of them and look at them. It'll be a lot easier to see if you have the models what's going on with those things. Okay.